All right. How's it going, everybody? My first video was I kind of just cut it off because it got really awkward. And I don't know how to edit videos, so I'm just gonna go through this manual bit by bit. Um, so this video, I'm actually gonna just go over this section called cylinder axis and the power. I don't know why this is being so weird. Cylinder axis and the power cross. This just explains the convention of how you're going to describe the spherocylinder stuff. And then at the end, we're going to go through this problem. Before that, I just want to start out by going over some definitions that I don't think were in the text. And I don't know if they were explained to you or not, but I'm just going to explain them anyway. Um, I guess I'll try to just type this. This is just stuff that Mandipal taught us. Two definitions that often get really confused with. They're different, but we often use them interchangeably. But these two definitions that I want to go over is torque and spherocylinder. And so torque is a surface with two curvatures, different curvatures that are 90 degrees apart. So really the key thing here to understand is that torque describes a surface, whereas spherocylinder, when we want to be accurate with the term, spherocylinder is a whole lens system that can be described as a sphere combined with a torque backside. Let me say this, as a sphere surface combined with a torque backside surface. So you can kind of see that a spherocylinder is a larger concept that includes the idea of a torque surface. So I don't know, really. Since this is a video, I'll just leave this here and you can kind of copy it or whatever. I don't even know how to do this, so. Oh, okay, I can save this. I'll leave this right there. Okay. And I'm done. Okay. So those are some definitions. And just to review some other things, some key concepts here for a plane cylinder. Just a cylinder, like a shape. Be sure to understand that there's no power in one meridian and maximum power in a meridian 90 degrees from it. This is just for the cylinder, like a shape. That, for example, we see right here, this cylinder. But of course, when we're dealing with spherocylindrical lenses, we're not really dealing with a pure cylinder. Instead, we're dealing with the spherocylinder definition that is right here. Okay, so I think that's all I wanted to clarify. The power meridian is maximum, like we would call it the power meridian, and then the power with no power is your axis meridian. Alright, so like I said, we're going to go through this convention. I'll just read it along. The orientation of a cylindrical lens is specified by the axis meridian. So what does that mean? The axis meridian is the one that has no power, right? So a lens with a horizontal axis meaning axis meridian, would be specified as x180, and a lens with a vertical axis meridian would be specified as x090. The cylinder power would then be oriented 90 degrees away. So for example, we have this cylinder here. Hopefully you can kind of see that the curve is, I can't trace this unfortunately, but the curve is not at 20. Like when instead the straight line, kind of like that line that I said you can trace with a finger and is straight, runs along the 20-degree axis. So that straight line is plano, meaning no power. And so you might have seen, when you think about prescriptions, the first number is associated with this axis. So this plano is associated with that number, meaning is plano at 20 degrees. So hopefully that makes sense. It's not that it's not like 5 is at 20, rather the plano, no power, is at 20, and then 5 represents the difference between that axis, in this case is plano, and the power meridian. And in this case the power meridian is 100, is at axis 110, because it's just 90 plus 20. So if I were to kind of draw the power cross, and we're going to explain power cross in a little bit, but if I wanted to draw the power cross of this particular image, then I would say that this is plano. Maybe you can even say it like at 20, whatever helps you understand what you're drawing here. And then because it's plano and the sill is 5, the difference is just simply 5. So it's going to be 5 at axis 1 excuse me, at axis 110. So these both are the same thing. Really, because it's plano, you don't technically need a number here. But like, to me, I think this is the more accurate description. So once again, this plano, this first number, is associated with, means it's at this axis right here. So the cylinder axis is specified in degrees from 1 to 180. So sometimes you might see this image that says 0 right here. It could technically also be 180. Like 0 and 180 are kind of the same thing. And a power cross, oh yeah, so a power cross, also known as an optical cross or lens cross, is used to show the lens power. So that's just what I did right here. Drawing this is really helpful. Oh, yeah, okay, I didn't even realize it was already in this image, or in this page. So drawing it really helps with visualizing the power meridian, the axis meridian, where they are, and what are the powers at those particular meridians. What does it say here? Note that usually cylinder is described with respect to the axis meridian, which is the one that contains none of the cylinder power. So I thought that was confusing at first. It takes kind of just a while to practice and understand like that cylinders are described in reference to their axis and not their power. So yeah, that's enough of that. Hopefully that makes sense. So we're gonna go through this problem here. It's pretty much the first problem in your book. So let's check it out. A cylinder lens n equals 1.5 has a radius of curvature in the power meridian of 10 centimeters, and the axis meridian is horizontal, axis 180. So this is a really important piece of information. Right off the bat, it tells you the axis meridian is horizontal. So if I were to draw the power cross, I pretty much try to draw these. These are 3 different representations of this description. So you're not going to have to draw this all the time, but this is a cylinder to show you kind of what the cylinder really truly looks like in its purest form, or in actual form. So the axis is the one, since this is a cylinder, the axis has no power, and it tells you here the axis is horizontal, so at 180. And then the power is always perpendicular, so here we have this at 90. We don't know what the power is, though, right? They don't tell you that, but they do tell you that the radius of curvature in the power meridian is 10 centimeters. So we don't know what the power is, but we do know that D equals n prime minus n over r. And r is equal to a positive, because it doesn't really tell you any indication that it's not. So r is positive 0.1 meters. Oh, I'm sorry. It says 10 centimeters, but if 10 cent, I can't even type there. 10 centimeters, you move it 2 decimal places to the left, gives you 0.1 meters. So when you do the math, and n prime is 1.5, and they I know it says n here, but n prime is the index of the lens, because we assume it's going from air to lens. When light travels from left to right? And so we assume that it's kind of going from air. Oops. I don't know why it's so laggy. From left to right. And so n prime is 1.5 and n equals 1. So then you plug that in, you get, I'm going to skip some math here. You get a positive 5. Okay, so that's positive 5 right there at the 90. And so here's the power cross, and then here is the visual representation of that, because now the power meridian is the one that's curved, right? And so we see this blue, hopefully you can see that it's curved like this. And so that is one providing that power in the vertical meridian. And since this looks like, I always like to imagine like those C-shaped kind of curves that look like this are converging rays. But it really, that doesn't, just because it's like that, doesn't mean it's a positive, because we don't know the index, because the index of refraction actually matters. So, just forget. Forget what I just said. It's okay. But anyway, we see that this blue thing is curved. So that's your power meridian. And then the axis meridian. This is a cylinder, so D equals 0. All right. So how do we approach this? Let's see what I can do here. So let's do some math here. We're going to use, this is probably the most useful equation ever that you're going to be using in optics. L prime equals D plus L, which really means n prime equals, n prime over x prime equals D plus C plus n. Why is my thing being so... My pen's not working right now. Alright, like that. And for our purpose, okay, so now that this should look pretty familiar for you, I forgot. So, but when we're dealing with cylindrical Spherocyl lenses, we want to be sure to talk about vertical versus horizontal. In this case, since the vertical axis, the vertical meridian has power, I'm going to say dV. That's what I like to write. So you can also write D90 if you want. So we don't, so n prime is actually going to be 1, because the image is still, you can assume that the image is still in air, right? Like the image is not, we're not dealing with n prime being 1.5 here because we're not trying to calculate the surface. We're trying to just find the image of the image, and the image is in air, so it's 1.0. And then we want to know where the image is. That's what the question asks. Yeah, sorry. It says, what is the location of the line image for a real point object at 50 centimeters? So that's this drawing right here, where we have, I didn't have a lot of space to write everything, but right, this distance is 50. And remember to write it's negative, because conventionally, if it's an image on the left side, it's negative. So that's your x, right? X equals negative, I'm going to say negative 0.5 meters, because we always want it in meters. So the d of the vertical is 5, and then n is also 1 because the object was in object space over here. So we kind of have n equals 1 and n equals 1. So hopefully that makes sense there. And then x is minus 0.50. Minus 0.50. And when you do all that math, x is going to be 0.33. X prime, the image location, is 0.33. And that kind of makes sense because this was a real object that, shined its rays towards this converging +5 axis, this +5 refractive surface. So if it's diverging its rays towards it, right, you expect that the plus rays to converge that back into real image. So you should expect a positive image location. So that's how we get 0.33 there. So what is location? Oh, an orientation. Well, the orientation of the line, I think is going to be too hard to draw, but instead think the power that refracted this light is vertical, therefore the orientation of the line is horizontal. Okay, so the line is horizontal. Yeah, forget it. This is just, I don't know why it's so laggy, I know, but the line is horizontal. I'm probably just using too much bandwidth. I don't know. Alright, so the next problem, or part 2, says determine the location and orientation of the line image if the object is virtual. So I'm just going to go ahead and make a new one. Yeah, well, I'll continue on this side because I have no more space. But now, I'm not going to redraw anything, but we still use this equation. We always want to use this equation when we're trying to predict an image or object location. Nice. I'm serious. I don't. Oh, okay. Sorry. Something's wrong with my pen. Now, so L prime, you want to use L prime equals D plus L. D is still going to be 5, right? This is kind of a different problem, but we're still using that +5 at the 90. We're not using this right now, so I'm just going to cross it out. This is a video, so that's cool. I don't really need it anymore. And so we have a plus 5. L is going to be 1 over what? The object is virtual. So this is one of those things where, let me draw this out. You have a plus 5 refracting lens, and since if the object was on this side, it would be negative. But since we have a virtual object, it's on this side, so that gives you a positive value here. And we want x prime. So here we go. This is 1, by the way. And then when you do all the math again, you get my pen's broken. You get x equals 0.143. So hopefully you guys got that. 1 over 7, and that's 0.143. All right, on to the next. Hope that was helpful. I'm going to try to figure out what's wrong with my mouse.